All right, so the last section in Chapter 8 that we're going to cover is Section 8.3, which is titled Hypothesis Tests in Detail. So some things that we want to be able to do are identify two possible sources of error in hypothesis testing, be able to distinguish between practical and statistical significance, and also identify similarities and differences between a hypothesis test and a confidence interval approach. Right? So the next slide I have here just revisiting small p-values, right? So what does it mean to have a small p-value? So a small p-value means that our test statistic is extreme, right? Meaning it's unlikely, unexpected. So an extreme test statistic means something is unusual and therefore unexpected. Therefore something unexpected has happened, right? So that's why a small p-value leads us to reject the null hypothesis, right? We're saying that this is unlikely to happen for our null hypothesis to be true, so we accept the alternative hypothesis, right? Or not accept, we believe that to be true, right? With this is statistical evidence suggests that to be true. Right? So if we have conditions that fail concerning sampling distributions of the C statistic, then remember we cannot find a p-value using the normal curve, right? The normal curve wouldn't make sense then. So there are two reasons suggested here of conditions that can fail for these reasons, right? One is the sample size is too small, and two, samples are not randomly selected. So in this case, conclusions may not generalize to the population. So with this, you may want to go out and get a new sample that's random and larger, right, if one of these were to fail. Right? So potential mistakes in hypothesis testing. So there are two possible mistakes that can happen. So we looked at a table like this before. So one mistake is if the null hypothesis is actually true, but we reject it, right? So we have like a false negative in a sense, right? So that is bad, right? And the probability of doing that is the significance level, right? We call this alpha, right? This box is alpha. But if the null hypothesis is true and we fail to reject it, that's good, right? That's okay. So then if the null hypothesis is false and we reject it, that's good. That's what we want. But if the null hypothesis is false and we fail to reject it, right, we didn't reject it when we should have, then that's bad. And that's an error we call beta, right? So essentially like a false positive in a sense, right? So like a false positive, like on a pregnancy test, right, would be that you're actually not pregnant, but the test didn't failed to reject that you were pregnant, right, in a sense, right? So saying you are pregnant, that would be like that example, right? So here's an example. So it says describing mistakes. Suppose the political analyst is interested in predicting whether a school bond measure on the ballot will pass, right? So here are our hypotheses, right? Our null hypothesis is that the population proportion is equal to 0.5, right? An alternative hypothesis is that it's greater than 0.5, right? Meaning that it would pass. So we want to describe two types of errors she might make in conducting this test, and be able to explain what a 5% significance level means in the context of the problem, right? So if we look at the next slide, these are the two, right? We're trying to describe two types of errors, right? So the next slide has two types of errors that could happen. So we could reject the null hypothesis when it's true, right? This means that concluding that 50% favor the bond when the actual proportion who favor the bond is 50% or less, right? So that could happen. And number two, another type, is that we could fail to reject the null hypothesis when it's false, right? So in other words, this means concluding that 50% or less favor the bond when the actual proportion who favor the bond is more than 50%, right? So those are two types of errors we have to consider in that context. So then the last question is, explain what a 5% significance level means in the context of the problem, right? So slide 7 explains that. So the 5% significance level means that there's only a 5% chance that the analyst mistakenly concludes that more than 50% favor the bond when in fact they don't, right? So that's our alpha level, right? So and if you can't remember, what that looks like, right? Remember going back to this chart, this is our alpha. So it's when the null hypothesis is true, but we reject it, right? So then you might wonder, how can we reduce mistakes, right? So it turns out that the only way to reduce the probability of both types of mistakes is to increase the sample size, right? Increasing the sample size improves our precision of the test, so it makes mistakes less often, right? So large samples are a good thing, right? We need large samples. That's one thing that we test for, right? Do we have a large enough sample? So the bigger the sample, stronger the test, right, essentially. And you might think, well, can't we just make the significance level really small? Well, it turns out we can't, because if we do this, then it increases the probability that we mistakenly fail to reject the null hypothesis, right? So there has to be this balance, right, between the significance level and the sample size for the hypothesis testing to work well, right? All right, so let's talk about statistical significance versus practical significance, right? So a result is statistically significant when the null hypothesis is rejected, right? So in other words, we have statistical significance when my p-value is less than alpha, right? We reject the null hypothesis, then we have statistical significance. So the difference between the data estimated value for a parameter and the null hypothesis value for a parameter is so large that it cannot be convincingly explained by chance, right? Chance alone doesn't convincingly explain this, right? So it's very unusual, right? But however, statistical significance findings do not necessarily mean the results are useful, right? So we have to consider that. So here's an example. So suppose the proportion of people who get a certain type of cancer is 1 in 10 million, and that a statistical analysis shows that talking on cell phones daily doubles the risk of getting cancer, right? So in other words, what that means is instead of 1 in 10 million that get this cancer, now we have 2 in 10 million, right? So just because we have statistical significance here, is it practically significant, right? So if we think practically, would the statistic cause a person to stop talking on a cell phone, right? Probably not, right? Only 2 in 10 million get the cancer if you talk on a cell phone daily. That is not a high enough risk, right? Not practical enough to be meaningful, right? So that's what it says here. Practical significant results is both statistically significant and it has to be meaningful, right? So this isn't really meaningful to us. It's not gonna change our routines. So slide 11 here says cautions about writing conclusions, right? So one thing is always true is we can never be 100% certain that our conclusion in hypothesis testing is true, right? So when our p-value is greater than your significance level, we want to avoid using the following phrases, right? So like we accept the null hypothesis, right? So that one seems to come natural, like you want to say that, but we should not say that phrase, right? We should also not say that we have proved that the null hypothesis is true, right? Because again, we can never be 100% certain, right? So instead, we should say phrases like, we fail to reject the null hypothesis, right? Or we cannot reject the null hypothesis, right? Or the statistical evidence suggests, the null hypothesis to be true. Or the statistical evidence suggests that the alternative hypothesis is true, right? So you can also say something of that nature, right? We can't say it's proved, but we can say the statistical evidence suggests that this is the case, right? This is the scenario. All right, so the next slide, we have confidence intervals and hypothesis testing, right? So these two things are asking slightly different questions, but they're very related, right? So a confidence interval asks, what is the value of this parameter, right? So if you want to be like 95% certain, what can the value of that parameter be within, right? Where a hypothesis test is asking, are the data consistent with the parameter being one particular value, or might the parameter be something else, right? So those are two questions that we're asking, but they're very related. So even though that these are designed to answer different questions, they are similar enough that they can lead us to reach the same type of conclusions, right? So we can actually do hypothesis testing through a confidence interval, right? So a confidence interval can lead us to the same type of conclusion as a two-sided hypothesis test, right? So a two-sided hypothesis test is related to a confidence interval, right? They're the most related. So here's an example. So we're going to conduct the hypothesis test, and then so we'll use alpha of 0.05, right? I believe is what I put in here. So then we're going to do a 95% confidence interval test and see how they can be related, right? So in 2009, it was estimated that 63% of Americans supported the death penalty, right? So in 2014, a poll found that in a random sample of 943 Americans, 538 supported the death penalty. So do we have enough evidence to support that the death penalty has changed among Americans since 2009, right? So previously we asked if it had declined, right? Now we're asking, has it changed, right? So we looked at that data before, but we're asking a different question, right? I'm just pointing that out. So step one, we want to do hypothesize, right? So our null hypothesis, remember, it's always P equals, right? So P equals 0.63. And then my alternate hypothesis, right, is what we're wanting to test is if P is different than 0.63, right? Or in other words, is P not equal to 0.63? So now we want to prepare. So previously we already verified that we have a random sample and everything is large enough to test, right? So we already checked those previously, so I won't check those again here, right? So then we need to compute the z-statistic and the p-value, right? So we can use technology to get those very quickly, right? I showed you how to do that in the last video, right? So our z-statistic is negative 3.78. My p-value is 0.0002, right? And you can double check that. So now we need to interpret. So if I use an alpha of 0.05, we're going to reject my null hypothesis, right? So there is support that the death penalty has changed among Americans since 2009. There's evidence to support the alternative hypothesis, right? So this is another way that you can do interpretation that's pretty easy to write, right? We can just say that there's support for this item, right? And that's what the alternative hypothesis was checking. So now let's make a 95% confidence interval, right? So a 95% confidence interval for this proportion would be 0.54 and 0.60, right? So again, I've shown you how to do this using technology. You can do that to get those values, right? So this would support then, right? Because what we're trying to see is if 0.63 would be in here, right? And this would support that this would support the same conclusion, right? Because 0.63 is not my confidence interval. It's not within my 95% confidence interval, so this would seem unusual, right? So since it's not in there, we would suggest that the population proportion has changed, right? That's what that would suggest. So to show you how they're related, right, let me draw a standard curve, right? So maybe between here and here is my 95% confidence interval, right? And if I'm doing a two-tail hypothesis test, then with an alpha value of 0.05, right? Then I'm also trying to see if my area here and here is less than 0.05, right? So if these two areas combined is less than alpha, right? That's my p-value. Then that would also be very related to my my p naught not to be within my 95% confidence interval, right? So that's how they're very related if we look at the bell curve, right? So the hypothesis testing is looking at the area where the confidence interval is seeing, is it likely that this would be within my confidence interval, right? So that's how that they're related. So here we have just StatCrunch results, right? So you might see printouts of like StatCrunch or R or so forth that will give you some statistics. So here's a stat printout of our p-value and our z-statistic, right? So you need to be able to interpret those if needed, right? And then here is for the confidence interval, right? So there's my upper and lower limit, right? And then this slide is just suggesting if we have confidence levels of this, which is just 1 minus alpha, then they correspond with the significance level, which is alpha, for a two-sided test, right? So if we have a 90% confidence interval, which is 1 minus alpha, then that gives a 10% significance level. So you can see how those are related, right? So if we're using alpha to be 0.1, that's similar to doing a 90% confidence interval, right? If we're letting p be 0.05, that's similar to doing a 95% confidence interval. If we do a significance level of 0.01, right, alpha equals 0.01, that's similar to doing a 99% confidence interval, right? So those two things are very related, right? All right, so that'll finish up this chapter, right? So we looked at population proportions. We looked at how to apply the central limit theorem with population proportions, how to do hypothesis testing with population proportions, right? So now what we're going to move into is looking at means, right? And doing some more confidence intervals, hypothesis testing, and so forth, right? So that'll be coming up.